Now we have known how to obtain the Nash equilibrium or Nash equilibria in a game. So after you have collected all the information about the game, about the players, what they know, their possible strategies, and all the payoff information, and you write down a payoff matrix, it can turn out that there are several Nash equilibria in the game available. And then we have to face the problem about which one to pick. Which one should we predict as the outcome? That's why we have this discussion of Nash equilibria refinement. We need to sort out at least which outcome is most likely to be played out by the players in a game. Let's look at this network scheduling game. It is a coordination game. So there are two television networks, both of them considering putting on a new reality show. Then they face this scheduling problem, whether they should put the show on Wednesday or Thursday. If both of them put on the same date, either Thursday or Wednesday, both of them will lose 10 because that will reduce the number of audience. They split the audience and make their show less valuable to the advertisers. So if they can put their show on different dates, Network 1 put it on Thursday and Network 2 put it on Wednesday, both of them will get 10 because then on different nights they capture the same group of audience, which is larger than half of that, and make the show more valuable to the advertisers. Before we try to find out the solutions or Nash equilibria in the game, let me explain my color scheme. So I have one red circle on network 1, so that's the player 1's color for their strategy choice. And network 1 will pick the best response for network 2's strategies. Here, when network 2 schedule on Wednesday, network 1 compare -10 and 10, circle 10, to say that when network 2 schedule on Wednesday, network 1's best response is to schedule its show on Thursday. And then if network 2 schedules on Thursday, network 1's best response is to schedule its own show on Wednesday. So the red circles on these payoffs are for the best responses of the players with the same colored circle. The blue circles the payoffs of the best responses for network 2, which also has a bigger blue circle on it. And again, same as network 1, as long as network 2 do not schedule on the same night as network 1 when it will put on the new reality show, network 2 is making the best response. So if network 1 put the show on Wednesday, network 2 put it on Thursday. If network 1 put it on Thursday, network 2 will put it on Wednesday. And now there are two cells in this payoff matrix contain the best responses from both players. So each of these green cells contain a blue circle and a red circle. These are two Nash equilibria. Facing these two Nash equilibria, we become the two-handed economist. We say, on one hand, if network 2 schedule on Thursday, network 1 will schedule on Wednesday, but on the other hand, there's another possibility that network 1 schedule on Thursday and network 2 schedule on Wednesday. So by far, as much as we have known about game theory, we cannot make a clear-cut prediction about what the two networks will do in this coordination game. One possible solution is to use the so-called chip talk. That is some pre-play communication. The players sort of talk with each other before they can officially announce which night they will put on the new reality show they're producing. And for this kind of pre-play communication to be chip talk, it should not directly affect the payoffs of this game. Otherwise, it won't be cheap. A chip talk can be useful only if the information conveyed in this chip talk is credible. If network 1 says, I will schedule the show on Wednesday, network 2 better believe network 1 will follow through this announcement. In this game, we actually do have that kind of incentive for both networks to tell the truth in the chip talk before the game officially starts. Because once they make their intention clear, it will benefit for both players if they can coordinate. Then if network 1 says, I will schedule it on Wednesday, network 2 will come out and say, most likely we will schedule on Thursday, even though we haven't decided yet. But eventually, when they officially announce which night they will schedule it, they will most likely to follow through. Because the payoff is much better if they can schedule it on different nights. Another situation is that, what if, yes, there are two Nash equilibrium, but there's one Nash equilibrium that is better than the other. Here, if network 1 can schedule it on Wednesday and network 2 schedule it on Thursday, both of them get 15 instead of 10 if they schedule in reverse order. Network 1 on Thursday, network 2 on Wednesday. That gives the networks lower payoffs than the other Nash equilibrium, the better one. And this is the so-called Pareto criterion. That means the players simultaneously select one solution or one single Nash equilibrium instead of undecisive about two different Nash equilibrium. Just pick one, and this one should be the better one or the best one for all players. So that is the Pareto criterion. As long as there exists a Nash equilibrium that provides the best payoffs to all the players will choose that Nash equilibrium as the outcome of the game. Again, if this is the situation, one best outcome possible for all players, we can refine the Nash equilibria into one single prediction. This next game is a design competition. Two architectural firms trying to compete to win a design. One is an established firm, the other is an upstart. If both of them choose the same style, the established firm will win. So if both of them decided to submit a traditional design, the established firm will win and the upstart will lose. If both of them choose to submit a modern design, the established firm will win it again. However, if the established firm choose to submit a modern design, but the upstart will choose to submit a traditional design, the upstart firm will win, and vice versa. If the established firm choose to submit a traditional design and the upstart firm choose to submit a modern design, the upstart firm will win. I have circled the best responses for each firms. For established firm, these best responses means that it's better to match the upstart's style choice. For the upstart, the best responses means that it's better to avoid what style the established firm will try to submit. So, if the established firm try to submit the traditional style, the upstart should submit the modern style. If the established firm try to submit the modern style, the upstart should submit the traditional style. On the other hand, if the upstart submit the traditional style, the established firm should submit the traditional style as well, and if the upstart submit the modern style, the established firm will try to submit the modern style as well. The sad news now is that there's no single cell in this payoff matrix which can contain two different colored circles. So there's no so-called pure strategy Nash equilibrium in this payoff matrix. However, the players can play a mixed strategy. That means each of them try to choose the style by flipping a coin. By 50% of chance, they choose either traditional or modern. This probability weight can change if these payoffs are different. It is because the symmetry in payoffs in this game so that the two strategies each have 1/2 of probability to be played out. If there's asymmetry in this payoff matrix for the two players, the probabilities put on the different strategies will not be 1/2. To see how to calculate this probability, you need to check out the appendix in this chapter. But that is not our focus here. Our focus is to understand why the mixed strategy can produce a Nash equilibrium. Why, when the two firms choose a 1/2 probability to play either strategy, they can achieve a Nash equilibrium. So now let's look at the expected payoff for the players. Let's say the upstart firm play this mixed strategy with 1/2 probability. It will play the traditional style with 1/2 chance. It will put the modern style into submission. And the established firm look at the expected payoff from the traditional style and the modern style strategy. So if it chooses traditional, the expected payoff is 1/2 of this 20 plus 1/2 of this -2, which is 10 minus 1. That is 9. And if the established firm look at modern, there is 1/2 probability to get -2 and another 1/2 chance to get 20. So the expected payoff for the established firm to play the modern style strategy is -1, 1/2 times -2, plus 10, that is 1/2 times 20, is 9 again. So when the upstart play this mixed strategy, the established firm face two different strategies give the same expected payoff. This makes the established firm feel indifferent between the two strategies. So if we put the expected payoffs into the payoff matrix, all these two players can see is that no matter what they do, they face the same expected payoff. So when the established firm is also playing the mixed strategy, play either traditional style or modern style strategy for the upstart firm, also give the upstart firm just expected payoff of 9. Both players are indifferent between choosing the two different strategies. That makes the mixed strategy Nash equilibrium an equilibrium. No player wants to deviate. Let's go back a little bit. Let's say if the upstart will put a higher weight of probability on the modern style, more than 1/2, or close to 1, or basically choose the modern style, then the established firm knows it should choose the modern style. As long as that probability is higher than 1/2, the established firm will choose to play this modern style strategy because that will increase its expected payoff. Let's say the upstart put 3/4 of probability in playing modern style strategy, and then the expected payoff for the established firm to play the modern style strategy is what? It's 3/4 times 20, which gives us 15, and 1/4 times -2, that is 0.5. So 15 minus 0.5, we got 14.5. If the established firm chooses to play traditional, the expected payoff is 20 times 1/4, that's 5, plus -2 times 3/4, that's 1.5. So it will be 5 minus 1.5, which is 3.5. So when the upstart put a 3/4 probability in playing the modern style strategy, the established firm look at an expected payoff from playing modern of 14.5, and the traditional is 3.5. So obviously, playing modern will be the best response to upstart mix the strategy of playing modern with 3/4 of probability. And then upstart realize that the established firm will prefer to play modern. What it should do is to play the traditional. That gives the upstart this 20 instead of this -2. So when the upstart put a 3/4 probability in playing the modern style strategy, it will actually want to change its strategy. That means the players want to deviate from what they have chosen to do. That is not an equilibrium. Only when the players facing same expected payoff from playing two different strategies, 9 for either styles and 9 for either styles for both firms, that is an equilibrium. That is how the mixed strategy Nash equilibrium works. And if you look at how they calculate the probabilities put on different strategies, that is exactly how we set up the equation to obtain these probabilities. So for this game that we find no pure strategy Nash equilibrium, we now know that we can find a mixed strategy Nash equilibrium as the predicted outcome. This next game shows us that there are some games they have both pure strategy Nash equilibria and mixed strategy Nash equilibrium. So let's look at the story here. There are two firms who would like to build gas stations at the same location, next to each other possibly, but that location can only support profitable operation by one firm. So if both firms enter the market or they build gas stations side by side at that one location, either of them will lose 2. If they do not enter, of course, they receive 0. But if one firm enter and the other stay out, the entrant will receive 1 as the profit. So is the case for firm 2. If firm 2 enter this market and firm 1 stay out, firm 2 will receive 1. That's the payoff matrix. Again, let's look at the best responses for firm 1 first. Conditional on firm 2's strategy, firm 2 do not enter 0 and 1. 1 is better, then firm 1 should enter this market. Conditional on firm 2 enter into this market, firm 1 compare 0 and -2, 0 is better. So firm 1 stay out. So the best response for firm 1 is that if firm 2 enter, firm 1 do not enter. If firm 2 do not enter, then firm 1 enter. For firm 2, it's the same story again. If firm 1 do not enter, firm 2 compare 0 and 1, enter is the better strategy. It's the best response. If firm 1 enter into this market, firm 2 compare 0 and -2, 0 is a higher payoff. So if firm 2 enter into this market, firm 1 stay out is the best response. In this payoff matrix, there are 2 green cells, which indicates the 2 best responses by both firms. Either firm 2 enter and firm 1 stay out, or firm 1 enter and firm 2 stay out. There are 2 pure strategy Nash equilibria in this game. But that is not the end of the story. There is another mixed strategy Nash equilibria in this game. In this Mixed strategy Nash equilibrium, firm 2 will play enter with 1/3 of the probability and 2/3 stay out. So then for firm 1, to stay out has an expected payoff of 0. It's 0 times 2/3 plus 0 times 1/3. 0 plus 0 is still 0. The expected payoff for firm 1 to enter is 0 as well when firm 2 put 1/3 on enter and 2/3 on do not enter. Let's calculate that. We use 2/3 times 1, that's 2/3, and 1/3 times minus 2, that's minus 2/3. So 2/3 plus minus 2/3, we have 0 again. So when firm 2 have this 2/3 do not enter, 1/3 enter mixed strategy, the expected payoff for firm 1 to stay out is 0, to enter is 0 as well. Now firm 1 is indifferent between to choose either stay out or enter. The calculation for firm 2's expected payoff is the same. Firm 2 also have expected payoff of 0 if it chooses to stay out or chooses to enter. So as long as both firms put 2/3 of probability on do not enter and 1/3 probability on enter, their expected payoffs are 0 for whichever strategy they are going to choose. That makes this set of probabilities on different strategies the mixed strategy Nash equilibrium. So now this game has 2 pure strategy Nash equilibria and 1 mixed strategy Nash equilibrium. The story is still that what kind of Nash equilibria we can get depends on the structure, the properties of the payoff matrix. And notice that the reason why we have 2/3, 1/3 on the 2 different strategies for these 2 firms, instead of have 1/2 and a half on the 2 different strategies, is because this payoff structure now is no longer as simple symmetry as the previous example for mixed strategy Nash equilibrium. In our first example, the winner in the design competition gets 20, the loser loses 2. In each cell, it's always the same story. However, in this entry game example, the symmetry in payoffs no longer exist. If both firms enter, both lose. If both of them stay out, they get 0. And if one enter, the other do not, the entrant will receive 1, the one stay out will get 0. Because of this asymmetry in payoffs, the probability to make the firm's indifference between the 2 strategies now is different from 1/2 and 1/2. In this game of complementary investment, we consider the role of incomplete information and bounded rationality. So our story goes like this. Google is considering to produce an operating system called Chrome OS, and Samsung is considering whether to launch a tablet computer based on using the Chrome OS operating system. If both firms invest in the new products, Google will get 20 and Samsung will get 20. That means these 2 products are complementary to each other. They will create a new market. Both firms will benefit. If neither invest, both of them will receive 0. If Google invests in producing the Chrome OS, it will receive 5 because there are still other hardware producers can produce similar tablet computers that utilize this operating system. However, if Samsung invested in producing a tablet computer based on Chrome OS, but Google do not really launch this product, then Samsung's investment will be completely lost. Samsung will lose 25. Let's first look at, with complete information, what the firms will do. Let's look at Google first. If Samsung do not invest in producing the tablet, Google compare do not invest in the operating system and invest 5 is the better payoff, so Google will invest. If Samsung invest in the tablet, Google compare 0 and 20, 20 is the better payoff, so Google will again invest. Now, invest is Google's dominant strategy. Do not invest in the Chrome OS operating system is the dominated strategy, so we can cross it out. Once that's settled, Samsung can actually simply look at when Google is playing the dominant strategy. Obviously, 20 is much higher than 0. Samsung will invest in the Chrome OS tablet. That is the Nash equilibrium of this game. If Samsung still want to think about what if Google do not invest in the Chrome OS system, it will compare 0 and minus 25, then 0 is the best response if Google do not invest in the Chrome operating system. However, actually, once in the reasoning, Samsung has realized that Google will never play do not invest the strategy. Samsung can only look at the strategy choice when Google choose to invest. When Google play the dominant strategy, this is called iterated dominance. And this Nash equilibrium is very easy to find out. This is one both firms know exactly what's in this payoff matrix, and both firms know the other player is a rational player and will play the dominant strategy. However, the information is not always transparent, and Samsung may not really know the payoffs to Google for do not invest and invest strategies in the Chrome OS. So, when Samsung do not have that information, it may have this belief that Google is very likely do not invest in the Chrome OS. Because Samsung believe Google will not invest in the Chrome OS, it will choose this do not invest to avoid this loss of 25. But Google knows that, so Google end up investing in the OS, and the equilibrium will be Google invest in the operating system, but Samsung do not invest in the tablet using Chrome OS. This outcome is also called a Maxmin solution for this whole game when, let's say, again, Samsung do not have the complete information about the payoffs to Google. We do not even need to assume that Samsung thinks it's more likely for Google to not invest in the Chrome OS. The only thing we need to know is that Samsung is just uncertain about what Google will do and not sure about these payoffs, the 5 and the 20. Samsung does not have that information about these payoffs. Another reason a player may employ the Maxmin strategy is that the player may have so-called bounded rationality. It does not have the computation power to figure out exactly what are the payoffs in this game and what are the best responses for the other player in this game. So that's another reason why Samsung, or say this particular player, may employ a Maxmin solution. If a player plays a Maxmin strategy, what this player does first is for each strategy, it finds out what is the minimum payoff to that strategy. Here, invest in the Chrome OS tablets will give Samsung a loss of 25, and do not invest will give Samsung 0. So the Maxmin player will say invest, loss 25, do not invest, 0. Then the Maxmin player compare the minimum payoffs between the two strategies. It will try to play the strategy that bring the higher or the highest or the max minimum payoff. In this example, it's between 0 and minus 25. Obviously, 0 is the maximum minimum payoff, between do not invest and invest. For Google, it can compare the minimum payoff first. The minimum payoff for do not invest is 0. The minimum payoff for invest for Google is 5. So compare 0 and 5. Google will choose 5. It's the maximum minimum payoff by playing either do not invest or invest. The result is that when Google and Samsung playing the Maxmin strategy, Google invest and Samsung do not invest will be the Maxmin solution. The Maxmin solution is suited for players when they do not have complete information and they do not have enough computation power to understand all the possible outcomes, to predict all the potential payoffs, to analyze their opponent's best responses. They may employ this kind of max-min strategy. The resulting equilibrium will be called Maxmin solution. Let me repeat the solution process for employing the Maxmin strategy again for a single player. When using the Maxmin strategy, the player first find out what is the minimum payoff for each strategy that this player can play. And then this player compare the different strategies based on their minimum payoffs and to select the strategy that give the maximum minimum payoff as the strategy to play. That is the solution process for Maxmin strategy employment. Finally, let's talk about the Nash bargaining solution. The Nash bargaining solution is a very different concept from the Nash equilibrium. When two firms are bargaining, two parties are bargaining, they're actually engaged in a cooperation. So if somebody starts to bargain with you, it doesn't mean that they are not interested in the deal. They are very interested in the deal. The only thing you need to worry about is how to make the deal a better deal for yourself. In the Nash bargaining solution, we first look at what is the disagreement point or threat point. It basically means when the two parties are playing a non-cooperative game. In this airline output quantity strategy game, we already know that if they do not cooperate, we will have this prisoner's dilemma outcome. Each firm earns 4.1. But if they start to bargain, it is possible they can make it to a better outcome. Because the Nash equilibrium is the default non-cooperative outcome, we use 4.1 as the disagreement point, or say the threat point. And if they can achieve different outcomes through bargaining, then their payoffs will be different from 4.1. What's going to happen is that we will calculate the surplus for each player for different outcome first. So for American Airlines, if an outcome is that American Airlines produce 64 and United produce 48, the surplus for American Airlines will be 5.1 minus 4.1, the disagreement point. That will be 1. That is the surplus for American Airlines. If the airlines reach this outcome, that's the surplus for Americans. For the United, this surplus is actually negative. It's negative 0.3. So when we times these two net surpluses together, we have 1 times minus 0.3. It's minus 0.3. This is a negative Nash product. This negative Nash product is less than when the firms are not cooperating. So obviously this will not be the Nash bargaining solution. The two parties, through bargaining, they're looking for the maximum possible Nash product value. And when one firm produces 48, the other firm also produces 48, each firm receives 4.6. 4.6 is 0.5 above 4.1. That means each firm receives a net surplus of 0.5. 0.5 times 0.5 is 0.25. Then what we have here is a positive Nash product. It is the Nash bargaining solution because it provides the highest Nash product in all 4 cells. Again, the Nash bargaining solution for a Nash bargaining game is to try to find the outcome that can maximize the Nash product.